Hi everyone. So in this bonus video, I just want to say a couple of things about why the amplitude of a bound state energy eigenfunction changes when the potential energy changes. And we talked about in class, right, how the uh, the the smaller the difference between the total energy and the potential energy is, the larger the amplitude of the wave function. So let's see why. So the setup for doing this analysis is the following. We imagine that we have some potential energy that's piecewise constant. So suppose that it's constant over here, and then it jumps to some other constant level here. And we're assuming that throughout this entire region, we're in a classically allowed region, so my total energy is greater than my potential energy. So here's the thing. You know that in such a region, we can always write uh, the wave function as, we know that it's oscillatory, and we might as well assume that it's sinusoidal. Right? So we can assume that this is a sine kx, and this is the spatial part of the wave function. Now you might be worried, well, how do I know it's exactly sine? We don't. But so this is an assumption. We could always generalize this argument by adding a cosine term if we wanted, or if we added like a phase constant in here, which would also do it. But just to keep things simple, I'll assume that the wave function has this sinusoidal form. The trick then becomes to think about how the amplitude might change across this point right here. So let's write that down. How does and let's call this point x naught. Okay. And I'm assuming that the wave function has the same general form, but with a different amplitude up in this region. So we know a couple of things, right? And so here are the things we know. So we know, right? So for higher v, so on the right here, we know that the wavelength increases, or that the wave number goes down, right? And that we got from analyzing the time-independent Schrodinger equation. We also know that we've got to apply a boundary condition here, right? That the wave function and its derivative have to be continuous at x naught. And so the trick is to try to come up with a relationship between the amplitude A and my wave number and the wave function and its derivative. And it's not maybe immediately obvious how to do this, but it turns out to be doable in the following way. Here's our question. Well, we know that the derivative d psi dx has the following form, right? If I differentiate this, I get a cosine and then a factor of k from my uh, from my from the chain rule. And so the idea is that we can also use a trig identity here. So so we know that there's a trig identity this Pythagorean identity, sine squared plus cosine squared equals 1. And we might get that, or something like this, right, if we square both sides of this. So if I square d psi dx, then I get a squared k squared cosine squared kx. But if I plug in my identity here, right, this gives me that cosine squared is equal to 1 minus sine squared. Okay. And if I multiply this through, right, then I get a squared k squared minus a squared k squared sine squared kx. But here's the thing, right? This is just k squared times our wave function squared. So but a sine kx equals psi of x. So this whole thing becomes a squared k squared minus k squared psi, and I'll write this as psi of x squared. And that, remember, equals our derivative squared. Now here's where we get to invoke continuity, right, and also recognize that we now just have a appearing in one spot, and depending apparently on the derivative, on the wave function, and on k. And so if we solve for a, right, we get the following. So I get, so let me just divide everything by k squared. So I get 1 over k squared d psi dx quantity squared equals a squared minus psi of x squared. And now I think you can see where this is going to go. Let me advance the page a little bit. And this gives me, so this gives me a, right, if I just shove this over and take the square root, I will get square root of psi of x squared plus 1 over k squared times my derivative squared. Okay, so, right, what we find then is here's where we invoke the continuity. But so by continuity, right, psi of x and d psi dx don't change at x equals x naught, right? We suppose that the amplitude does, right? But then the only thing that can cause the amplitude to change is k. But k does change, right, causing a to change. Right, and moreover, what we find is that for smaller k, as I decrease k, right, I'm going to make, because it goes in the denominator here, I'm going to make the second term larger, which is going to mean my amplitude increases. And that's exactly what happens, right, when the potential energy goes higher. We get a smaller k, right, and that's how you can argue. So when v gets larger, and then in our setup here for x greater than x naught, a increases. So this is still a little bit more, a little hand wavy, but hopefully this is helpful for convincing you why the amplitude increases here.